I am pleased to introduce my colleague and friend, Scientia Professor Martin Green. I first recognized the value of Martin's work and at an IEEE Photovoltaic conference in San Diego in 1980 when he announced a breakthrough in voltage of 30 millivolts over anything, my students are all laughing, 30 millivolts over what was previously done. By 1983, they had their first world record efficiency of 18% and had continuous world records till the 25% result in 2008, which wasn't surpassed until 2014. So a major history of world records. But even more important is the founding of the School of Photovoltaics and Renewable Energy Engineering at UNSW. And this was actually started in 2003 with 125 undergraduate students and 4 faculty members. It has since grown to, I have to look at my notes, over 400 students, undergraduate students, 190 graduate students, of whom 90 are PhD students in photovoltaics. And we have, instead of 4 faculty members, we have 25 faculty members, including 6 full professors, and 47 fellows and researchers, 24 professional staff, and it is the biggest by far and the healthiest of the photovoltaic programs in the world. And we all owe a lot to this program and what it's done for us. So I introduce Martin.
Thank you very much, Alan. I've been asked by Paula Mintz to give a talk at the Photovoltaic Silicon Valley chapter of the IEEE. So I'm actually recording this talk in Sydney, but I'll be available at the end of the talk live to answer any questions that you might have. As Alan mentioned, I'm Martin Green from the University of New South Wales, and I'm Director of the Australian Centre for Advanced Photovoltaics, which involves the university as well as other groups from around Australia. What I'd like to talk about today is to address the question, how did silicon solar cells get so cheap? If we look at what's been happening in recent power purchase agreements such as shown here, you can see that on the vertical axis is the price that was bid in terms of dollars per megawatt hour, which is a common way when you're talking about power at the bulk level. The highest axis ordinate there is 140, is it? Can't quite see it too clearly here, but it just shows the last couple of years the types of bids that have been going in many parts of the world. If you look at the top line, the orange line there, that's a fit, a rough fit to the prices that have been for silicon photovoltaics, and the blue line is for wind energy. So over the last year, something quite dramatic has happened. For a long time, wind has been the cheapest form of renewable energy, but over the last year, there's been such a dramatic drop in the price of photovoltaics that it has underbid wind in some of these recent bids. So the most recent bid was in Abu Dhabi, and there the photovoltaic systems were bid at $24 per megawatt hour, which is a really low price for electricity supply, below even the incremental cost of generating electricity from coal. In the bid before in Chile, there were a range of other technologies that were bid in the same process, and one of those was coal, and the photovoltaics in fact came in at half the cost of new-fired coal generation. I guess the main reason these costs have been coming down is the cost of the hardware itself have been reducing, in particular the cost of the module. This shows the cost and price of manufacturing a module such as shown in the diagram there in terms of US dollars per watt over the last 6 or 7 years. So the red line at the top shows the average selling price for the module. So that's like the wholesale module price, and you can see that it's come down quite dramatically. The other data points there, they show what manufacturers report as their manufacturing cost. So some of them are using different conventions here, so they're not all directly comparable, but it gives you an idea of how manufacturers think their costs have been reducing. So we see, quite a dramatic cost reduction. Over recent years, so if you look at the 2016 type figures, you'll see that there's quite a difference between the price and the cost, about a 20% difference or so. And that's the margin that manufacturers make on selling the modules. You need that positive margin to cover other costs not included in the manufacturing costs, like selling costs and administrative costs and a whole lot of other costs associated with running a business. So you need a healthy margin to not only to meet those costs, but also to allow the industry to grow, to invest in R&D and to build new facilities and so on. The other point I'd just like to make while I'm on this slide is the green data points at the bottom, I guess your bottom left of that diagram, refers to costs reported by First Solar, who manufacture thin film modules. All the other data points are for crystalline silicon modules. And you'll see, around 2010, the cost of making a thin film module was very much lower than that of making a crystalline module. So we all thought back then that thin film technology was the way to go, because obviously, First Solar had demonstrated you could get much lower costs. But if you follow that line along, you'll see that around 2012, there was a crossover, and crystalline silicon manufacturing costs actually undercut the thin film. So that's changed perceptions. Perhaps crystalline silicon can become cheap enough that it will be difficult to be matched by thin film technology. So a change in outlook there. And one of the reasons for that is First Solar manufactures a unique technology. It has to do all the improvements in the technology itself, whereas with the crystalline silicon, there's a huge industry working towards ongoing improvements, making it an ongoing moving target that any technology supported by only a single company has trouble matching. Okay, well, what I'm going to do is try and underpin the costs for the reason for those recent cost reductions, and I'm going back quite a ways to the beginning of photovoltaics. So this is Edmund Becquerel, who's generally credited with being the discoverer of photovoltaics in 1839. He had some quite simple apparatus there with a couple of metal electrodes in a solution, and he was able to demonstrate that light could be converted into electricity with that process. So that just sort of provided the stimulation for a lot of the activity that followed. The real progress, however, happened in the 1930s, almost a century later, with the development of quantum mechanics. And this paper here by Alan Wilson was the first to address the properties of semiconductors, applying this newfangled quantum theory to trying to understand its behavior. And the theory he developed and published in this paper here is pretty much the same as you find in a modern textbook, but you get bands of allowed and forbidden energy, and the forbidden gap is what's important in producing a solar cell. Not only was there progress in the 30s with understanding the physics of semiconductors, but also in understanding the semiconductor devices. And Walter Schottky, another European, was very instrumental in pinpointing the reasons you're getting this photovoltaic conversion occurring in these semiconductors. And he pinpointed the interface between the metal and the semiconductor as being the active region of the device and so on. It was all a bit confused between them. So the diagram just shows a typical type of solar cell from that era. The really big push forward, however, came in the US at Bell Labs in the early 1940s. Russell Ohl here was experimenting with silicon for some microwave detectors, but he was producing some very pure silicon by solidifying material in a crucible shown there, which is very much like the modern process for producing multicrystalline silicon. He had the purest silicon he could find, but it still had quite a few impurities in it. And when he cut segments out from the solidified mass, like as is shown here, and shone light on it, he could actually observe a photovoltage. So, trying to understand what was causing this photovoltage led to the discovery of the role of impurities in silicon and how some gave N-type properties and some gave P-type properties. So N and P just stand for negative and positive, and they were the negative was the material that became negative when you shone light on the device, positive, the bit that came positive. So that was the simple terminology that was used there. But trying to understand that effect was really, heralded in the birth of microelectronics. So, the role of dopants in semiconductors, p-n junctions, and so on, that underpin the operation of all subsequent silicon semiconductor devices. So with the rapid development of technology that insight stimulated, the first efficient silicon solar cells were made a few years later. So all the processes for controllably introducing impurities into the material, making contacts and all that kind of technology was developed. And this trio here made the first efficient silicon cells in 1953 and published in 54, but they're made on little semicircular wafers of silicon that you can see there, and had what we would now call an emitter wraparound sort of geometry. The terms the emitter and the base just stem from the transistor theory that was being, was the main driver for the development of the microelectronics industry, was the development of transistors and so on rather than cells, but they benefited from that development. So that breakthrough made it to the front page of the New York Times. They reported here, fast power of sun tapped by battery using sand ingredients. And there was hope, immediate hope for applications such as shown as the upper right hand side there, providing power for use by families and so on. However, that wasn't to be. The cells were so expensive back then that the only application found for them was on satellites, which was an application that was growing rapidly at the same time. So the first cells appeared on this Vanguard satellite in 1958, and this Telstar 1 was the first satellite to beam TV signals across the Atlantic. But there was a big developmental effort of the cells to provide the best possible cells for that application. Again, most of that effort occurred at Bell Labs, and that took cell efficiency up close to 14% by present standards, with a fairly simple cell structure shown here, which became the standard for the next sort of decade, as you can see from this line here. So a lot of effort was put in to develop that cell, and then people were satisfied with it. In the 1970s, there was a lab, ComSat, Communication Satellite Lab, established in the US, and its role was to try and reevaluate satellite technology with the growing emergence of satellites and so on. So they had a look at the solar cell technology and made a couple of improvements based on techniques that have been developed in microelectronics in the interim. So using lithography to define fine metal patterns and thinner diffusions into the surface and so on, they were able to produce what was called the violet cell, which gave the first jump in efficiency for about a decade. And then anisotropic etching had been used in microelectronics for things like V-groove transistors and stuff like that. And they applied that technology to texturing the cell surface to form these pyramidal textures on the top of the cell shown there. And this was called the black cell because it looked like black velvet, essentially. So big jump in efficiency from that texturing process, as you can see. So that established an efficiency, probably close to 17% by present standards. This was the same period that there was oil embargoes in the US, and it was really hard to find petrol in the US, as this queue of cars here might indicate, but petrol became very scarce in the US. So the US started programs to look at developing new energy options to make them energy self-sufficient. And this was a program that was initiated by Richard Nixon, but followed through by Ford and particularly by Jimmy Carter, the three subsequent presidents. So, a bipartisan sort of program. But Jimmy Carter in particularly was interested in the solar energy aspects and put a lot of resources into developing solar technology that I'll talk a little bit more about. So that was one of the significant contributions, I think, to the present situation where we have low-cost cells. About the same time as the black cell was discovered, a way was found to apply the contacts more simply than the vacuum processes that were used commercially to form this cell structure here, which is now probably most commonly known as the aluminium back surface field cell. The back surface field refers to this P+ layer along the rear here. But This was first reported by Eugene Ralph, who was a researcher or a scientist at Spectralab in the US, which is still a company that we work with, supplied the cells for our recent 40% efficient module. But this was reported at the 1975 IEEE conference a few years before I presented my first paper there that Alan referred to in the introduction. But Eugene reported this sequence here, which got rid of the vacuum processes and allowed the metal contacts to be prepared by a screen printing process. So that was the first time that that process had really been demonstrated that it could produce cells of reasonable efficiencies. At about the same time, the program I mentioned, trying to develop energy sources, initiated by Nixon right at the end of his term, but carried through by in a bipartisan way by the next two presidents, started what became known as the flat plate solar array project. And the idea of that was to reduce the cost of photovoltaics by over 100. So the cells at that point in time were 100 times too expensive to find wide-scale use. So that, that was the sort of stated aim of the project, find a way of reducing the costs. And this is Elmer Christensen here, who actually met at the time, but he is holding a type of array that you could buy commercially in 1975 in his hand there. And the big arrays at the back show that the type of progress that was made over this 10 years of the program. So the program was terminated during the Reagan administration, who Reagan wasn't particularly keen on renewables. One wonders what might have happened if the US had have kept going with the strong program that had been initiated in the Carter administration. But one aspect of these programs, which was probably the most important aspect in terms of the legacy it left, was block purchases of modules, so that US manufacturers would be asked to supply modules meeting various specs to the Jet Propulsion Laboratory who was managing the program, and then they'd be assessed for their suitability by the program, and suggestions made for improving their performance and so on, feedback given on how well they were going, and testing devised to try and work out the limitations of the module. So the standard IEC test for modules, they derive from this era. So by the end of this program, the testing was pretty much in its modern form. So again, the little module over here on your left is one of the better modules supplied in Block 1 purchases. Elmer is holding another Block 1 purchase there. And then, as the purchases went on over the 10 years, the modules got bigger and better. So initially, many of the modules were covered with this sticky silicone rubber material, and it was found that that didn't have the requirements to stand up to hail or attack by birds and things like that. So the glass-covered module became standard, and Spectralab actually introduced this, not only screen printing, but also this other idea of a laminated module that eventually became the standard for all the modules purchased in the block purchases. So by the end, this module was probably purchased in 1984, but looks pretty much like a modern module with the monocrystalline cells sort of squared off, and to improve the efficiency of the module, and pretty much size of a present module, except the cells are 4 inches rather than 6 inches square. That was a really important program, and as I said, that I think the main legacy was developing a standardized module that was durable and could last. Some of the modules installed around that era have been shown to have lasted, well over 20 years, some of them 30 years, and so on. So the designs that were developed during that program turned out to be very durable. Around that era, these are two systems that were installed in 1981 towards the end of that program, but this one here on your left is in Australia, and this was in fact the largest commercial sales of cells in that era. So there was 13 of these repeater stations beaming telephone signals in the outback of Australia, but these 13 arrays, each of about 1 kilowatt, that 13 kilowatt order was one of the largest commercial orders of that era. many manufacturers were selling into demonstration projects like this one. So this is the Rancho Seco nuclear plant in Sacramento, and this was a 1 megawatt solar system installed adjacent to it. The original idea was to cover the whole isolation zone for the nuclear plant with photovoltaics, but it was never followed through, although there's a lot more in the area now, and the Rancho Seco nuclear plant has been closed down. Another thing that was looked at under the program was the residential use of photovoltaics. So there was a number of these regional experimental stations made where manufacturers sort of put in dummy roofs with photovoltaics, a lot of house monitoring of houses in the vicinity to see if the loads match. Some isolated houses installed, and then the plans were to go to this incredibly large demonstrations here of 100 homes. So that just seemed mind-boggling at the time, 100 homes connected with photovoltaics. How great would that be? Australia just recently passed the 1.5 million homes, so things have come away since then. I guess then, as I mentioned, the program was curtailed during the Reagan era, and the momentum shifted away from the US overseas. So initially it was to Japan. So Japan was particularly interested in this residential use because not having much land available for large ground-mounted systems, the building mounted systems sort of made sense. So this was a big system that was put in on Rocco Island in '86. I actually visited it then, but there was like 200 of these dummy solar rooftops installed at Rocco Island, and this was a facility operated by CREEPI, which is the Japanese Power Industry Association, research association for their power industry. So CREEPI was testing these systems to see if there's any issues with connecting them to the power grid. And they tested them a few years, and the conclusion was there wasn't any reason why you couldn't connect large numbers to the grid. So the Japanese then just launched their what was called the Million Roof program. So it started in '93 and '94. And in that year, the world production was 60 megawatts. That was the total production worldwide, not just from one line like it is nowadays, but accumulated production worldwide. They actually installed 70,000 roofs by the year 2000, and the idea was to have 1 million by 2010. So that'd be about 5 gigawatts. So that was just a mind-boggling quantity back in 93-4 when that program was announced. So you got partly there. So the mechanism they use, this graph shows the number of amounts of kilowatts actually installed within Japan, and quite small before the program started in 1994. The subsidy started. The red dots show the percentage subsidy over here. So it started about 50% subsidy, so the government would pay half the cost of your photovoltaic system. So as more people got interested and the number of systems installed increased and the cost of installing them went down, the subsidy got progressively reduced. So there was more and more systems going in, but subsidy quite low. What was quite interesting was by 2004, the subsidy had dropped to below 10%. I think it's 7% of the total system cost. So it was getting quite small, and the total amount of subsidy being paid by the government was actually decreasing, even though the number of systems going in was increasing because it had become such a small fraction. But you'll note even with less than 10% subsidy, the number of systems was going up, was still increasing. But then I've seen it written that it was due to pressure from the power industry, people like TEPCO that brought us Fukushima and so on. They were worried about the increasing penetration of photovoltaics and the market issues that arise from that. So their lobbying power was greater than the PV industry, so they managed to have the program curtailed. And even though the subsidy had been quite small, you see an immediate drop in the number of systems being installed once there was no subsidy. So I guess the message there, like even if you give a little bit of incentive, it can have a big impact. So that was the message that I took away from that. That program, the US had been dominant in photovoltaic technologies through the 80s and early 90s, but the Japanese program sort of took the momentum away from the US, as shown here, increasing market share. Then the emphasis shifted to Europe, as shown by this orange line here, which is the German market share of production. The Japanese ones started progressively slipping once the program, the subsidy was terminated. The reason for the interest in Europe really, well, the interest really started accelerating after Chernobyl in 1986. And you know, you can see why. You know, this is the radiation dose as it spread over Europe. So I guess it was quite a frightening time to be in Europe when this radiation was spilling over into the country and you had no idea where things were going to finish off. But that sort of increased European resolve to develop alternatives. And at the same time, you know, the global warming was becoming a more serious issue. So, you know, my recollection is that Chernobyl sort of predated the interest in global warming, and this sort of graph here, you know, sort of confirms it. So, you know, the dotted line is newspaper reports of global warming, and they started a year or two after Chernobyl. But the two issues combined to accelerate interest in photovoltaics. So the Germans in particular experimented with a number of programs to promote the use of photovoltaics through the 90s, but the really successful program was their feed-in program that started at the turn of the century. So the idea here was just to offer money for each unit of electricity supplied to the grid. So someone installing a photovoltaic system would just get paid for the electricity they supplied at a rate that was supposed to be high enough that, you know, you could make a business proposition from installing the system. And this program was very successful. You can see the market picking up very, healthily during these early phases. Then it started getting out of hand. It just sort of was becoming too big. So the German government was trying to control the amount installed by steadily reducing the amount for the feed-in tariff. So in the end, the reductions were coming quite quickly, and eventually in 2013, they were able to reduce the feed-in tariffs low enough that it sort of, stopped this out of control increase in the number of systems being installed that was happening. So up to 7.6 gigawatts was installed in 2012, which was far more than the German government really wanted. So a very successful program. What this provided was a steady growing market for manufacturers of cells, and a market where the cells could be sold profitably because the feed-in tariff was enough to, you know, allow a decent price for the photovoltaic modules. The technology leadership moved from the US, after the end of the Jet Propulsion Laboratory program, and it was here in Australia that we started setting the records for silicon cell efficiency. So the first record was 1983, and this was, we made an 18% efficient silicon cell there, which was clearly higher than where ComSat had got to. And this is the team that were involved with producing that record cell. So we weren't much bigger than that. It was only quite a small team, but you'll recognise Stuart there. And Ted Spidlak. Those two were very important in the development of the PV industry and the subsequent cost reductions, as I'll outline a bit more further on. The other important player here was Ji Chun, who was from China. He was one of the first Chinese scholars to be let out of China when Deng Xiaoping relaxed the policy in relation to interchange of scholars and so on. So he joined us in about 81, so one of the first of 1,000 or so scholars that got released under that program. But he was a huge success, worked hard and contributed to the effort. So created a very positive attitude towards Chinese scholars within our group, I guess, as a result of that experience. We actually held the record for silicon cell efficiency for 30 of the last 33 years. So those little red dots correspond to that regime. And ended up with the PERC cell shown here, passivated emitter and rear cell. And this is just a projection from the International Technology Roadmap, the latest edition, but just sort of showing their projections as to how the industry might evolve. But the aluminium back surface field approach that was developed at Spectralab in the early 70s is expected to slowly get phased out by these higher efficiency approaches. The PERC cell technology that was developed at UNSW, a heterojunction approach developed at Panasonic in Japan, and then the interdigitated back contact cell developed by Rich and Swanson's group at Stanford, most notably. So presently, PERC is supposedly occupying about 20% of 15–20% of market share. Prior to the PERC, though, there was an earlier technology that was licensed from the group here, and that was the buried contact solar cell, which we began licensing from the mid-1980s onwards. And our most successful licensee was BP, who became the largest PV manufacturer in the 1990s. But they marketed what they call the Saturn cell, which we knew here as the buried contact cell shown here. This was the first big installation in Toledo in Spain, and me standing very proudly at the front of it here. But there was a megawatt of solar panels installed in this field. It was Europe's first megawatt system, and most of them were UNSW technology. The reason I'm mentioning that is my first visit well, it wasn't my first visit to China, but the first visit with a technology, with cell fabrication in mind to China was in 1994. And it was the idea of David Hogg, who was with Unisearch, or now New South Innovations. And his idea was, seeing we were making these cells that were more efficient than anything else on the market, if we could manufacture them cheaply in China, we'd have the market sewn up, because the quality of the cells would be undeniable because they were better than anything else on the market, and we imagined we could do it quite cheaply in China. So we took one of our promising postdoctoral researchers, Zhengrong Shi, along with us to act as translator. So we didn't realise that it might have been better to have him doing all the business deals at the time, but his role was as translator. But it was just completely hopeless, our assessment of China in that era. So there was absolutely no infrastructure there, and a long way from being able to put our plans into action. So we just said, no, China's hopeless for PV manufacturing. So that was the impression we were left with. Instead, we took a different course. As I mentioned, everyone thought thin film was the answer, so we developed our own thin film technology, crystalline silicon on glass, set up a factory in Botany for producing it. This is Ted Spidlak again, who became acquisitions manager for the factory, buying the equipment and so on for it. But it proved to be a training ground for the Chinese industry. We actually got some of these thin film panels on the market. So there's fields like this operating around Germany, hopefully to the present day, that have megawatts or sub-megawatt quantities, or near megawatt quantities of these panels operating in them. So it should be about 10 megawatts out there somewhere. But as you'll see, the reduction in the crystalline price has squeezed a lot of thin film manufacturers out of the business, including us. But this was the staffing at Pacific Solar, and we had recruited a lot of students and postdocs, etc., from the University of New South Wales, but we also recruited a lot of people directly from China because of the strong Chinese representation amongst our researchers. We felt quite comfortable in dealing with Chinese researchers and could communicate and so on through our Chinese researchers. So we actually did some active recruiting from China during that period. And as I said, this provided the training ground for a lot of the subsequent industry that established itself in China. So, this is just where many people from there ended up within the industry, showing the little logos of the companies involved, but many of the key players within the Chinese industry. So it was a really well-run operation headed by David Hogg, but we got like ISO accreditation, so good management systems in place. And Paul Bassor was one of our employees who would be well known in the US. But he established design of the experiments, methodology, and a lot of quality control type measures that were embedded into the staff that were listed here. So it was a good training ground in modern management and production technology, I guess. In 2001, Zhengrong said he wanted to go back to China. You know, I still had this impression of China from the 1994, so I thought he had very little chance of being successful there. And, you know, things hadn't changed a lot, but they had changed sufficiently that he thought the situation, you know, may be more conducive to establishing photovoltaic manufacturing there. So there wasn't any infrastructure there, so it wasn't a trivial thing to do, but he managed to set up this production line in Wuxi near Shanghai. And in 2002, 9th of September, we actually had this opening of the first 10 megawatt production line. So Zhengrong was there. He was chairman of the board and also CEO of Suntech. He was also their chief translator. He was translating for me as I gave an opening speech. I think he was their chief accountant. He was the best at about everything the company did. So Gala opening as indicated. The other important people that were important was Ted Spitalak, who helped with the equipment procurement for Suntech and its commissioning and so on, and training staff. And Stuart, who went over and used our virtual factory tool to help train the many shifts of engineers that worked on this line in cell processing and quality control and so on. So you know, we had a big impact into the establishment of this line. And I guess it's successful beyond our wildest dreams. So this is just a timeline of Suntech development, and this shows the different investment stages, if you can read it there. But it was actually established on a shoestring. So Zhengrong managed to attract, and his co-founders, which included a few people from a group here and from Pacific Solar, managed to raise 6 million from the local government through the help of the local government. And Zhengrong stuck in 2 million, in some of it cash, some of it IP, you know, into the venture. So very, you know, talking about small bickies here in terms of the money involved. But by 2005, the company was able to make the cells so cheaply that they could sell profitably, and with the profits invest in new manufacturing capacity and so on. So they didn't need huge capital injections to grow because of the profitability, the fact they could undercut the manufacturers outside of China, you know, in these early days. But around 2005, things had grown to the stage where, you know, Zhengrong wanted to grow even bigger, and more capital injection was required. So he engineered what is termed a management buyout. And in a management buyout, the management of the company raises the capital to pay out the additional investors in the company, generally through cash provided by a new group of investors. And this is what occurred here. So there was this group of international investors. Goldman Sachs was probably the most prominent, but they gave Zhengrong enough money to be able to buy out the original investors at a handsome profit to them, and in return these new investors got shares in the newly formed company. This proved to be very profitable for both the old investors, who made about 10 times their original investment, and the new investors, who also made about 10 times their original investment. Goldman Sachs, for example, made over 200 million from this deal by my calculation. Suntech itself did an initial public offering on the New York Stock Exchange, shown here, a bit more detail here, and that raised about 400 million, which is a massive amount, you know, compared to the $6 million and so on that Zhengrong had started with. So this is the big day in December 15th, 2005. Zhengrong actually listed the day before, but you can see Stuart Wenham there and myself. We got to help ring the bell on the dais. But Zhengrong had done a number of important things. He had established the first viable private cell production in China. There'd been some production by state-owned companies, but it was like in little dribbles. They were some of the companies we'd visited in 1994 and hadn't been particularly impressed. The other thing that was really important was he established a competitive position internationally for Chinese modules. So the German market was then growing very rapidly, as I showed in one of the earlier graphs. So he managed to sell the modules onto that market there. He helped build up a local supply chain to reduce costs. So initially there was no supplier of low iron glass in China, for example. So Zhengrong actually imported glass from Sydney for his first modules, but he helped industries like that establish in China by providing finance or prepaying orders and things like that, just to help them industry get started in areas that were critical to his supply. And then the most important thing was raising capital on the US exchange. So this was the first private Chinese company to list on the US exchange, and it was reportedly the largest technology float of 2005, with the 400 million odd that was raised in that process. I'll probably have to speed up. I'm going a bit slower than I thought I would. But that triggered a whole avalanche of activity within China. So, Zhengrong was a pioneer by a couple of years, as you'll see, but there was a whole lot of activity, and because I guess the interest in developing photovoltaic manufacturing in China came from two directions. One was from the Chinese-based companies that could see what Zhengrong had done and wanted a piece of the same action, and the other was from the US venture capitalists that could see how much money Goldman Sachs made from that deal, and they wanted to do something similar. So there was this mutual interest supporting each other to cause this explosive growth in, company establishment in the PV manufacturing space in China. We were closely involved with a lot of it at the University of New South Wales, because part of the due diligence done by the US investors was, showing the Chinese companies had contact to good technology, which meant to us. So a lot of our former students and researchers, particularly those that could speak Chinese, got snapped up very quickly to assume senior positions within the growing industry. So the red or orange bars, they're just so people that left here and got involved with Chinese companies. So the red ones I showed there were actually companies established. So the team that established Suntech actually went on to establish Sunergy and also JA Solar. So the team just sort of bounced around China, combining with other Chinese partners, as well as grabbing additional researchers from here to repeat their first company establishment. So 3 of the 4 first companies to get into serious manufacturing in China were actually companies established by a team from here, with Ted Spitalak playing a prominent role in that. Okay, there's a lot said about Chinese government involvement. Like if you read many press reports, you get the impression that the Chinese government decided to establish the industry by handing out huge loans to get the industry started and so on. But it was actually, it didn't really happen that way. There was local government involvement, much as would happen here, like being a lot of fighting over aluminium smelters and things like that in Australian history, trying to encourage them to set up in your local government area. But the same type of thing happened in China. So from 1994, which is the year that we visited with PV manufacturing in mind, the situation in China changed a bit, and there were strong incentives for local governments to establish local manufacturing activity. The local government got to keep some of the taxes that companies would pay if they were successful, and also the local government officials got promotions depending on how well they'd done in doing that. So sort of a double attraction in establishing companies. But even though that scheme was in process, Suntech had to bounce around for several local governments before they found one willing to back them. So even that scheme was in operation. They weren't desperate to fund new companies. You had to put up a really strong case, and Suntech founders had to work hard to find a local government that would back them. So after the Suntech IPO, that just completely changed the situation. So everyone had read about this solar billionaire. Zhengrong owned enough shares that the shareholding was worth over $1 billion after the float. Everyone got excited within China, and these local governments said, well, this is a great industry for us to attract to the area because, it's growing quickly and the companies are profitable and, obviously an industry of the future. So just about every local government in China decided to establish PV manufacturing within their vicinity. So this uncoordinated, irrational exuberance, as one commentator has expressed it, created what I call the third wave of activity for photovoltaic. So the first wave, I didn't have too much time to talk about it, but they were the companies established before Suntec started doing well. Then a second wave got established because they could see how well Suntec was doing. And then this third wave was established through local government support, as indicated here. So I visited many local governments. I did a lot of travelling around China in that era, but just about everyone presented plans like this of, this huge manufacturing facility that was going to be established in their local government area. We'd get up to 5 gigawatts manufacturing in the next few years. So that created, a growing proportion of the world production was from China, the red line here, but it also created enormous oversupply within the industry, which has been important to the cost reductions. So that oversupply stressed the supply chain, I guess. So this is the polysilicon prices. So that was the first thing to suffer. There wasn't enough polysilicon produced worldwide to supply all the manufacturers who wanted it. So the price just skyrocketed, as shown here. And then in response to that, new facilities were started and new companies got into PV manufacturing, and then the opposite happens, as it often does. You get an oversupply. We go from an undersupply of the material to an oversupply, and the prices drop very low in recent years as a result. Equipment, this is equipment sales, mainly to China. These are the customers. So the red bar shows China that dominates. Taiwan's the other big player there. But that just skyrocketed as all these local governments were supporting companies to establish. So got up to $10 billion in 2010-11. But most of the equipment was getting supplied from Europe and North America, as indicated here. I won't go to this in any detail, but around 2010, there was a lot of modules getting imported into the US that was creating a lot of consternation there. But that trade was more than offset by the amount of equipment that was being supplied by the US to China and the amount of polysilicon, which was where the US had a real technical advantage being supplied back to China. So in fact, there was a net export of product from US to China in this era, which is quite unusual in that this was the same time as the US initiated trade war against China, worrying about the huge number of modules that were coming in. But not a good situation to initiate a trade war when your balance is in your favour. But anyhow, that's what occurred. If we look at the prices, this top line here shows the average selling price of the modules. This is the silicon component, and this is I guess that's the manufacturing cost of the module, as I showed earlier. And the light blue region is the margin. So, over this post-Suntec IPO period, modules were quite expensive, but healthy margins for the manufacturers. The silicon supply issue came to a head, and then prices dropped, and that sort of was largely responsible for this first big drop in prices. And then oversupply situation, you'll see the light blue region starting to disappear. That means most companies were unprofitable over this period because they had to sell below cost to keep the cash flow, to keep them cash coming in. And then we've entered a more stable region where there's a small but stable margin for most manufacturers now. But quite interestingly, like the last quarter, or this quarter, the average selling price for modules will be about 40 cents a watt. Back 8 years ago, it was $4 a watt. So really the price of the modules has come down by a factor of 10, or 90%'s been taken off the cost over an 8-year period. That's real. But the main issue, the main reasons for that are the transfer of the industry to China, where the manufacturing cost was very much lower than in other parts of the world. Then the oversupply situation in China that forced manufacturers to evolve very rapidly in their cost structure, or else face the risk of being wiped out, particularly over this period here. So very rapid cost reduction drives by the manufacturers to stay in business. The federal Chinese government didn't get involved until after 2009. So if you remember back to that graph showing Chinese growth in the industry, this was after the event. So it wasn't really federal government involvement that drove the Chinese growth. It was this local government support. When the Chinese federal government did get involved, it tried to rationalise the industry by picking winners. So it tried to give support to those companies that looked viable, and it gave that through lines of credit, and let the others flounder. So the idea was to pick winners, give them support so they could survive, and then let fate look after the remaining players. Okay, so these lines of credit were quite large, billions of dollars, but they weren't particularly attractive to manufacturers and only small uptake. So these are often cited as the reason the Chinese industry grew so quickly was these massive loans from the federal Chinese government, but they really came in after the event, and they weren't particularly attractive to the manufacturers, although undoubtedly have helped some manufacturers stay in business in tough times. That brings me to the last slide. So, how have solar cells become so cheap? So, this is my take on it. So it was sort of like a government industry cooperation that achieved the outcome. So there were some very important government programs. So the US, the flat plate solar array program was really very important. That 10 years of funding produced a standardized, reliable module design and methods for testing them and so on. There was other technical innovations like EVA, ethyl vinyl acetate encapsulation that's almost universally used, was developed in that program. The aluminium BSF approach was developed before the program, but it was sort of consolidated in the program. So by the end of the program, everyone was using that technology. Multicrystalline silicon, that was the first sort of commercial sales of multi-silicon panels, was during that program, so that got firmly established. And the fluidized bed reactor, which is grabbing a larger share of the purified silicon market as a lower cost technology, it was developed during that program as well. So there was a number of notable outcomes from it, but probably the standardized module design was the most important. In Germany, the feed-in tariff EEG program, particularly over the 2001 to 2012 period, the program's still going but in diminished form, but over that period it was really important to the industry in providing a reliable, profitable market for this growing industry. And Australia played a role. So our group here at the university has benefited from various centres of excellence type programs offered by the Chinese government from 1981 to 2010. And that provided the expertise that underpinned the manufacturing diversification from expensive manufacturing countries to low-cost regions of Asia. So that's been important in the price reductions as well. And then China, this uncoordinated initiative by the local government, huge amounts of money wasted on equipment and so on that you saw in those equipment sales, but those haphazard initiatives were very important in creating the oversupply situation that had accelerated the cost reduction within the industry. And then number of private players. So Chinese companies, they were all private companies. They're all regarded in China as wholly foreign-owned enterprises because they're registered in places like the Cayman Islands and so on, so they're not Chinese registered companies. And then US investors, through their willingness to support Chinese companies, particularly pre the global financial crisis, their strong support for Chinese companies then allowed the industry to thrive. So thanks very much for your attention. I'll be pleased to answer any questions now and then in live for the attendees that are in the US at the moment. Thank you very much.
See Alan walking up. Any questions here? Dun, dun, dun. Go on, Renata, you look ready.
Where do you think the next stage of development is going to be, or the next stage of growth in the market?
Yeah, well, I think like what I would like to see happening. What is happening worldwide is there's still plans for many new coal-fired stations to be installed. Like there's something like 1,300 gigawatts of coal-fired plants that are in this planning stage, particularly in emerging economies. So I think they're the countries that are really important for photovoltaics to gain a firmer foothold. So it's happening to some extent in China, like China's got the largest program now in terms of installing photovoltaics, and that is certainly displacing to some extent their need to install more coal-fired power stations. So that's good. But part of the reason for the Chinese interest in that is that there's local manufacturing in China, and by supporting the installation of photovoltaics, they're also supporting local industrial activity. So that I think if we can get that occurring in other countries, we might see the same outcome. So India is very keen to install more solar, but probably hampered by the fact that they haven't got any manufacturers that are yet competitive with the Chinese industry. So I think it's important to try and establish local manufacturing in as many emerging economies as we can to sort of get this local incentive to install photovoltaics rapidly to try and displace the installation of coal-fired plant. So I would see India as the next large market, and then you sort of work down the chain. There's obviously a strong interest from Southeast Asia in general in developing their power supplies, and in Africa ultimately I guess that'll be the large market for photovoltaics.
Any more? If not, then we'll thank Martin and wish you well in the future.
Thanks, Darren.